Welcome, ladies, gentlemen, and everyone in between or not even on the spectrum to the ICRAR Weekly Astro Talk. We're going to have to come with a better name for that, I'm absolutely sure, very soon. But that's our talk. Gentlemen, and everyone in between, ladies and gentlemen, on the spectrum. First things first, I'd like to acknowledge the traditional custodians of the land, with a better name for that, I'm absolutely sure, Noongar land, and pay respects to elders past, present, and everyone in between. Ladies and gentlemen, this talk is from ICRAR, the International Centre for Radio Astronomy Research. We are a research organisation across two nodes, two universities, Curtin University and the University of Western Australia. We're also part of Astro 3D, the ARC Centre of Excellence in All-Sky Astrophysics, and unifying over 200 world-leading astronomers to understand the evolution of matter, light, and elements of the Big Bang to the present day. Now tonight we're going to be joined by Dr. Fiona Panther, who's from UWA, the University of Western Australia, who will be telling you everything about antimatter. Now tonight, hello, Dr. Fiona.
Hello there. It's very nice to be here, and I'm looking forward to chatting a little bit more about this mysterious thing that we call antimatter. Hello there. It's very nice to be here, and I'm looking forward to chatting a little bit more about this mysterious thing that we call antimatter. Hello there. It's very nice to be here, and I'm looking forward to chatting a little bit more about this mysterious thing that we call antimatter. Hello there. It's very nice to be here, and I'm looking forward to chatting a little bit more about this mysterious thing that we call antimatter. Hello there. It's very nice to be here, and I'm looking forward to chatting a little bit more about this mysterious thing that we call
what's going on?
Hello there. It's very nice.
We have some tech issues. Sorry.
Yeah, no, I'm just it's fine with me. I'm just seeing if David can lend a hand at all.
We have some tech issues. Sorry.
Yeah, no, it's fine with me. I'm just seeing if David can lend a hand at all.
We have some tech issues. Sorry.
Yeah, no, it's fine with me. I'm just seeing if David can lend a hand. It wouldn't be fun if it worked.
Tech issues. Sorry.
Yeah, it's time, right?
Absolutely. It'd be boring. Life should be boring.
Gotta live on the edge sometimes. It wouldn't be fun if it worked.
Absolutely.
Yeah, it's time, right?
Absolutely. It'd be boring. Life should be boring.
Gotta live on the edge sometimes. It wouldn't be fun if it worked.
Absolutely.
Yeah, it's time, right?
Absolutely.
David says it's working.
It should be boring.
Gotta live on the edge.
If you heard it, if Cass heard it, hang on, it may be because I had it on my screen for a second.
It's coming through with about a 30-second delay, but it's live and working.
Okay, from the top, people. Let's do it again. Woo! Awesome. Okay, let's do this then. Tell me when you're ready. Give me a thumbs up. Hello, ladies and gentlemen, for the first time ever, this is not a repeat, and welcome to the Astro 3D ICRAR Weekly Astro Talk. First things I'd like to do is acknowledge the traditional custodians of the land in which we're speaking, the Whadjuk Noongar land, and pay our respects to elders past, present, and future. This talk is from ICRAR, the International Centre for Radio Astronomy Research, a research organisation across two universities, Curtin University and the University of Western Australia. We're all about discovering the hidden universe through radio astronomy and secretly lots of other different types of frequencies as well. We won't go into that right now. We're also part of Astro 3D, the ARC Centre of Excellence in All-Sky Astrophysics, unifying over 200 world-leading astronomers to understand the evolution of matter, light, and elements from the Big Bang to the present day. So just a small area of study. But it won't just be Fiona Panther. Dr. Fiona, hello.
Hello, lovely to be here this evening.
Fantastic. And just to whet everyone's appetite, what will you be talking about?
So tonight I'll be talking a little bit about something that people may think is actually science fiction. but it's not. It's science fact, and it's antimatter.
Awesome. Awesome. Well, that's great. I'm very excited by that concept. Before we move on to your conversation, though, I would like to talk about something else, that whether it's science or whether it's not, whether it's science or is it art, sometimes science produces amazing pictures, amazing plots, amazing graphs that almost look, well, artistic. I mean, let's face it, science is a human endeavor, and therefore science in itself is quite artistic. So we have a picture on the screen right now, and is it science? Is it art? Is it both? Listeners, watchers, people, audience members, and of course, Dr. Fiona, what the heck do you think this might be?
Well, whatever it is, I think it definitely counts as art. I am gonna hazard a guess. There must be some kind of science there. It reminds me somewhat of those very zoomed in images of insect wings or hairs.
Yes, I was going to say, it looks chitinous or chitinous. It kind of looks like, yeah, an exoskeleton of some sort of animal. If you pull back, it's going to be some horrible monster, like from the microscopic world. That's my guess. And ladies and gentlemen, if you have a guess, you can go to the ICRAR Twitter account, so @ICRAR, and you can put in your guesses, and we'll let you know on Friday what it actually is. So you can get involved right there. Or if you want to throw your ideas right now, put them in the comments, and our wonderful helpers, Kirsten and Cass, will be able to see if you're right. And you won't win fabulous prizes. No fabulous prizes tonight, except the knowledge that you're right and everyone else is wrong, which is a prize all in itself. All right, but enough of this tomfoolery. Let's pass it over to Dr. Fiona, talking about all things antimatter.
Thank you very much, Greg. And it's lovely to be here tonight talking about, this is one of my favorite things to talk about. I did my PhD studying antimatter in our galaxy. So it's really nice to be able to share this with everybody. So a little bit about me first. My name's Fiona, and I am an astronomer who has worked at ANU initially, where I did my PhD, and then I worked at UNSW Canberra. I did a postdoc there, and I recently, just about 3 weeks ago, this is my 3rd week working at UWA, and I used to work more on antimatter and looking at gamma rays. And now what I'm doing is I'm searching for gravitational wave signals coming from things like merging neutron stars. And we're trying to do something really, really cool with this, is we're trying to see if we can tell people that there's going to be a neutron star merger, those mergers between binary neutron stars, before they actually happen. So sending early warnings out about these very, very important events. But let's talk more about antimatter. And the title of this talk is called, Where Did All the Antimatter Go? When we look around us, everything we see is made up of ordinary matter. So you and me and the chair that I'm sitting on and everything around you is made up of matter, not antimatter. But we know back at the Big Bang, everything was created then. And in principle, based on the laws of physics we know, there should have been equal quantities of matter and antimatter. And the fact that none of the universe around us right now is made of antimatter says there's probably something we don't fully understand about the laws of physics. But antimatter, people tend to think this is some kind of science fiction thing. You've probably heard of it in things like the Da Vinci Code. There was a big storyline around antimatter, and it was made out to be this very scary thing. And what I'm going to tell you about tonight is to kind of demystify and make more of the facts about antimatter available to you, and then you can go and share some of this information with your friends, with your family, with your school friends if you're still in school. But in order to understand antimatter, we have to start with matter. So these are the things that we are made up of. So a human being is made up of molecules, and then if you get down further and break those molecules apart, you get down to single atoms. And if you break those down further and you go inside the atom, you find these subatomic particles. Now, every single one of these subatomic particles, either they can be broken down further, or they are as small as you can possibly get. And these are the particles which make up what we call the standard model, or the standard model of particle physics, to give it its full name. So this describes all of the particles that exist and what makes these particles interact with one another. So these are the force carriers. So on the left-hand side, we have matter particles. So the ones down the bottom, or there's one down the bottom you might see, that's the electron. That's a nice familiar one. That's part of the outer part of the atom. And electrons are what give us things like the brilliant colors that you see from stars and things like the background behind me. That's all coming from electrons jumping around in their host atoms. But if you go down further into the center of the atom, you find these weird things called quarks, or quarks, depending on which particular pronunciation you want to use. You can use either. So an atom contains up and down quarks, and if you combine these in the right ratio, you can either get a neutron or a proton, and those are what make up the atom's nucleus. And what you can see here is there are some other particles which we might not be so familiar with. There's a one there which is called the neutrino. That's an extremely light particle. In fact, if you hold up your thumb right now, there are billions of neutrinos streaming through your thumb, which are coming from the sun. And there are other types of quarks that you can see there as well. You've got ones with some quite funny and rather silly names, the charm and the strange. But these are the things which make up all of the matter in the universe. You, me, planets, stars, galaxies, all made up of this matter. And then on the right-hand side, you've got these force carriers. These are particles which tell the matter how to interact with itself. So for example, when the electron binds to the nucleus, it's the photon which is telling those two things to attract one another using the electrostatic force. That might be a term that you may be familiar with. Now, the important thing to notice here is that all of these things are matter, but I haven't shown you anything yet, which is antimatter. So what is antimatter? So put simply, antimatter is kind of like matter's twin. They have very similar properties, so don't mistake antimatter for dark matter, because these still interact using the same force carriers. And the other thing is we actually have detected antimatter, it's particles, so we know it's real. But what makes them different is if you have a negatively charged normal matter particle, your antimatter counterpart will have a positive charge. So for example, the electron has an antimatter twin called the positron, or positive electron. And the really cool thing about this is if you have an electron and a positron which come together, they will do something called annihilate. And what annihilation does is it takes all of the mass of those two particles and it converts it to pure energy. So this is the most efficient energy generation process in the universe. So if you wanted to make a super efficient power station, you just have to find some way to make matter and antimatter interact. And annihilation sounds quite scary, but it's really not. So if you actually had some antimatter hit you right now, you probably wouldn't notice. So from a single particle, an electron is so tiny that you don't actually get that much energy out of just one or two electrons. You'd have to get a whole massive, enormous chunk of antimatter to actually do any substantial damage. So where does this discovery of antimatter actually come from? Antimatter is really interesting in that it was not discovered through experiment initially. It was actually discovered through theory. So this gentleman here is Paul Dirac, and he's a very famous physicist and mathematician. And he came up with this really interesting equation which describes how electrons interact. So you don't need to worry too much about what that equation is telling you. But what you do need to know is that this is the equation which enables us to hold up a mirror to the ordinary matter in the standard model and reveal antimatter. And this lovely quote from Dirac I really like, and it says, "God used beautiful mathematics in creating the world." Dirac was a very famous atheist, but this was kind of almost an ironic kind of quote from Dirac. But I think even just looking at that equation and the symbols that it uses, I think it is actually a very, very beautiful equation. So that mirror, if you want to put this in technical terms, this equation has positive and negative energy solutions. Positive energy is matter, negative energy is what we think of and conceptualize as antimatter. So how does this actually work? Now, if you're looking at classical physics, particle energies can change smoothly. So if you have a particle which is wanting to go down to its lowest, you've got an excited particle up here, and it's trying to lose some energy, it has to go smoothly. Quantum mechanics is special because it allows particles to move in discrete jumps. And the thing is, in classical physics, if you move smoothly between energy levels, you can't get through that zero energy barrier. Quantum physics actually enables that to take place because rather than having to go smoothly, the particle just jumps from a positive energy level to a negative energy level. Now, when that negative energy level is not filled, that is what we actually conceptualize in terms of math as antimatter. It's not quite correct in its physical interpretation. And the reason for that is because we managed to find a particle which has all of the properties required by Dirac's equation to satisfy it, to find a solution. And this is it here. This is actually an image of the very, very first piece of antimatter detected and reported in the literature by humans. And it was discovered by this man, Carl Anderson. And this is a nice quote I like from Carl Anderson. And it says, "The ideal student would be one who was not working for grades, but was working because he was interested in the work." So if you are interested in maybe pursuing physics at university, or you're in school and there's something which really excites you, keep this quote in mind, because this is how you find something that you're really passionate about and you want to pursue going forward. But back to this image. So what this shows is something called a cloud chamber. And these two dark tracks here that you can see, there's a one curving upwards and a one curving downwards. These are very fast moving particles. So you have some radioactive things which bombard this strip through the middle, it's lead, and it's spat out. Look at the one going upwards, and it curves upwards. And what Anderson deduced was that this had exactly the same properties, the mass, as an electron, but it had to have the opposite charge. And the only thing which satisfied that at the time was Dirac's theoretical idea of this antimatter particle. And so this here is the first reported discovery of a positron. An interesting aside to this is actually that there was a discovery of a positron earlier, and it was several years earlier, and it was made by, there were two. There was one in Russia and one in China. And these discoveries were actually made by PhD students. The students discovered these positron tracks in their cloud chamber images and took them to their respective advisors. And in both cases, the advisor said, "You probably did something wrong. I don't believe it. It's just an electron and you got something mixed up." So this is an example of how easily you can be thrown off the right track when you're discovering something. And this is why science is so tricky. And it's such a shame that those discoveries didn't end up getting reported. But we do now recognize them in the literature. So what about antimatter in our universe? Where is it? Is it there? Can we see it today out in space? So all of the known laws of physics today say that during the Big Bang, you have to create equal quantities of matter and antimatter. So just so we're not getting confused, this is a pie chart, and it shows that you've got this, what we recognize that there's this whole chunk of matter that we call dark matter. That's something we don't understand. We don't know whether it's a particle or not. We don't know what forces it interacts with. So it's not antimatter. But what I'm talking about here with antimatter is that cyan chunk in the lower pie chart during the Big Bang. The atoms, that's the matter. So that makes up today about 4.6% of the universe. But if you looked at all known laws of physics, we should think that half of that has to be antimatter. But that, doesn't really work, because if this was the case, either all of the antimatter is hidden somewhere in a distant corner of the universe, or we wouldn't be here today. And the reason for that is because of this thing called annihilation that I described earlier. So during the Big Bang, the universe was a lot smaller. So if you imagine a balloon that's filled with matter and antimatter and it's all really close together, it's all going to find each other really, really quickly, unless there's some big spatial separation between the two. And the reason why we think that we don't maybe know all of the laws of physics, that maybe there's something we don't understand, and that there may be some antimatter or more matter created in the Big Bang than antimatter, is because of this. So let's say that there was equal quantities of matter and antimatter created in the Big Bang. This means that there must be somewhere in the universe a chunk that is made only of antimatter. So could you have somewhere entire clusters of galaxies, billions of galaxies potentially, made up of antimatter, anti-atoms making anti-stars and anti-black holes, which is a strange thing to think about, but hypothetically, it's just like ordinary matter. It can collapse down just like matter collapses down to form a black hole. So could this be true? How do we test this and, do some science to see if this is actually the case? Well, we don't think this is the case in the nearby universe that we can see, because we would see the antimatter annihilating on the boundary between the antimatter cluster and the ordinary matter cluster. So here's our hypothetical antimatter galaxy. I'm saying it's hypothetical. This is just an image of a galaxy that I've pulled from Google Images. And here is the boundary between the cluster of galaxies it belongs to and the ordinary matter universe that we know. And along this boundary, what you would have is you'd have electrons from the ordinary matter finding positrons, and you'd have atoms finding anti-atoms. And what would occur is they would annihilate, and that's what's represented by this diagram down here in the bottom corner. This is called a Feynman diagram. And what you see is you get an electron interacting with a positron, and you get some gamma rays that come out. And we have very sensitive gamma ray telescopes that would be able to detect this if it was happening. And we haven't seen it so far. So what's the conclusion here? Well, what we think may have happened is that there may have been some imperfections in that mirror between antimatter and ordinary matter in the standard model. This has a technical name. If you want to look it up, it's called CP violation, or charge parity violation. I'm not going to go into detail, but what it means is that during the Big Bang, there was a lot more matter created than antimatter. This is something that was somehow inherently baked into the laws of physics. And that's why you end up tipping the scales very far in favor of ordinary matter. And bringing it back to Dirac, who discovered antimatter, this is something, a quote that was quite prescient. And it says, at the beginning of time, the laws of nature were probably very different from what they are now. And so what he's saying is that maybe there was some special condition during the Big Bang that tipped those scales in favor of us having a matter-dominated universe, and a universe made up mostly of matter. So our universe is mostly made of matter. So where can we find antimatter today? The answer is just a little bit closer than you might think. In fact, you may even have an antimatter source in your house right now. Funny, it's a bit bananas, but a banana contains a tiny amount of an isotope of potassium called potassium-40. An isotope is a type of a particular element that has a different nuclear structure. And some of these isotopes are just a little bit radioactive. Not the kind of radioactivity that's going to harm you. This is no greater than any normal background radiation. But this particular type of potassium is quite special because when it decays, and every potassium-40 atom has a probability of decaying, and it turns out that you get about 1 decay every 75 minutes in your standard banana, and it will produce a positron, and it'll kick a positron out. That doesn't go very far because, of course, it goes into the banana, and the banana is made up of lots and lots of electrons, and it annihilates almost instantaneously. So it would be very, very difficult to actually harvest any antimatter from your bananas. But it's kind of cool to think about that you've got this thing in your home which is producing this almost science fiction sounding thing right now. And it's really not that scary. I mean, everyone eats a banana every so often, right? So the interesting thing about bananas as well is that with this small amount of potassium-40 in them, they've become a really good measure of how much background radiation humans tend to be exposed to. In fact, there's a measure of radiation absorption that we call the banana equivalent dose. And that is the amount of radiation that you would get from consuming 1 banana. And it's all coming from this potassium-40. So if you're thinking of like funky units that are a little bit strange, that is one to remember, the banana equivalent dose. Another place where you get antimatter is in something called cosmic rays. So these are very fast-moving, energetic, charged particles that are coming from outer space, and they bombard the atmosphere of Earth all the time. So some of these cosmic rays are made up of positrons or antimatter. So some examples here is you have these mesons, these pi mesons. These are made up of half matter and half antimatter. They don't live very long. They're very, very unstable, and they do eventually decay. We have positrons, which I've already talked about. The anti-electron, those are being produced in cosmic rays all the time. And you also have these things called anti-neutrinos. So I kind of told a bit of a lie earlier on when I said to hold up your thumb and you had all those neutrinos coming through your thumb. I didn't want to scare you because those neutrinos that are streaming through you right now from the sun are actually anti-neutrinos. So all of the nuclear reactions that happen to make the sun light up in the very center of the sun, they actually produce anti-neutrinos. So that's kind of a cool thing. In fact, you know, you've got antimatter going through you right now. So these cosmic rays, one of the places these are thought to come from, these are quite cool, and they're called pulsar wind nebulae. So what these are very fast spinning neutron stars, and it's this bright blob here in the very, very center. This is a funny looking image. This is made in gamma rays. And as the pulsar spin slows down, so as it spins slower and slower, it breaks itself down, and all of the energy it loses, or at least some fraction of it, you actually get converted into pairs of electrons and positrons. And these get streamed out above and below the poles of that spinning neutron star. And what's happening in this image is the neutron star in the center, this bright blob at sort of the pointy bit of this bow shape, it's moving towards the left-hand side of the screen. And it's streaming behind it these big, long tails, some of which will be made up of electron-positron pairs. So that's one of the sources of antimatter that we tend to look at in the context of looking for it in our own galaxy. This is Jaminga. This is the Jaminga Pulsar Wind Nebula. Most of the antimatter on Earth, though, is made in bulk at CERN, and this is the home of the Large Hadron Collider. And a lot of the experiments on antimatter are carried out in Geneva. Here in the experiments, you are producing a lot of antiprotons. And what happens here is you produce the antiprotons by smashing things together, and then you slow them down, and you can actually store them for a while by confining them in a magnetic field. There's a special type of antimatter container, which is called a Serco trap, was invented by a Dr. Serco, And what happens there is the antiprotons kind of get bounced around a magnetic field and confined. If you've seen the Da Vinci Code, the device which is used to trap the antimatter there is loosely based on this very, very real thing that we do actually use in experiments. And what's happening there is they're actually testing whether the laws of physics are the same for matter and antimatter, because this is something that we don't actually know. So if you have an anti-atom, is the spectrum that you get out the same as the spectrum you'd get from an ordinary atom? So if you were to look at, say, the spectrum of hydrogen and antihydrogen, would those two things be the same and indistinguishable, or would they somehow differ? Another thing that they're trying to test is, does antimatter fall down or does it fall up? Because one thing you may be aware of with the standard model of particle physics is it doesn't actually involve anything related to gravity. It's completely disjoint from gravity. And so the Dirac equation doesn't tell us anything about how antimatter interacts with gravity. So one of the things that they are testing there is whether antimatter falls up or whether it falls down. So firstly, the anti-atoms. What happens here is you very carefully combine the antiprotons and positrons to make antihydrogen. So a regular hydrogen atom is a proton and an electron, and an antihydrogen is an antiproton and a positron. And what they then do is they make measurements of the spectrum of antihydrogen. So looking at the types of light it emits from those positron transmissions. And this is an experiment called ICRAR. It's quite an interesting experiment. And so far, they haven't detected any difference between the spectrum of hydrogen and antihydrogen. But they still have more experiments to do. So, keep posted. You never know, we may find something a little bit unusual. And then there's the case of gravity. So what we do here is you now want to try and drop your antimatter to see whether it falls downwards under the influence of gravity, or whether there's some kind of anti-gravity effect which allows it to go upwards. And the experiment where they're doing this is called AEGIS, and it's not yet fully clear whether it does fall down or up. And I've just seen in the chat that apparently it's angels and demons that had the antimatter trap, not the Da Vinci Code. I apologize. I am not up on my Dan Brown books. It's been a while. I am very, very sorry to any Dan Brown fans out there. I do apologize. But no, back to gravity or anti-gravity. It's not yet clear whether antimatter falls down or whether it falls up. So maybe this could help us invent those hoverboards that everyone's been so desperate to have. And finally, antimatter does actually help us. So we do use antimatter in the detection of cancer through something called positron emission tomography. So if you were to do a regular CT scan, this is just using X-rays. You may have had one in the hospital. They're very, very quick. You go into the little thin tube and they quickly scan you. In this case, in this CT scan you see here, the liver looks nice and healthy. But when you inject something which emits positrons into the patient, and it actually gets attracted to the cancer because the positron gets attached to a glucose molecule. Cancer is very, very hungry. It loves to chew up glucose at a very, very fast rate, much faster than surrounding tissue. So all of those positrons get concentrated into the cancerous cells. And what you see here is in that liver, you can actually see that tumor shining. And that bright patch there is coming from gamma rays, which are emitted when the positrons annihilate there. So antimatter does help us. And you may know somebody who's had one of these scans. It's a very, very important diagnostic tool. So just to finish up, and then I will answer any questions that you have. We think that almost all the antimatter that was made in the Big Bang probably annihilated not long after. And the reason for that is because there was just so much more matter than antimatter that it just wiped it out. But there is a lot we still don't know. We don't know how it interacts with things like gravity. We don't even know if the laws of physics are the same for matter and antimatter. but it definitely can help us understand that beautiful mathematics that describes our universe. So thank you very much for joining me, and I'm happy to answer your questions.
Thank you very much, Dr. Fiona, for that really interesting talk on antimatter. To start the questions, I have a question, so I'm going to leap in and abuse my host privileges by asking a question. Can you get is antimatter valuable, and could I like buy all the bananas in the world and make my fortune by getting the antimatter out of them?
I love that question. Antimatter is extremely valuable.
Yes.
So in terms of the Large Hadron Collider, it takes so much energy to make antimatter, because if you think about it, when you annihilate antimatter, you get energy out, and it's the most efficient energy generation process in the world. And to get antimatter, you have to put energy in, the equivalent amount of energy to what you'd get out, in fact, a little bit more. And because our energy generation processes aren't that efficient, things like power stations that use coal or oil or even nuclear power, they're just not that efficient. It costs a lot to get that much energy. So could you use bananas to make fortune? It would be very, very tricky, because the banana is made up of very, very dense material. So when you emit just one positron every 75 minutes, you've got to find some way to get it out of the banana without it interacting with any matter. So to give you a bit of perspective, out in space, a positron that is emitted in the solar system would maybe live for about 10 seconds. And that's out in what we think of the vacuum of space. So imagine here on Earth, where it's not a vacuum at all. So it would be very tricky to get them out. But if you could, then I think Australia could have a really good industry, because of course we do produce bananas. So maybe we've got an antimatter factory on our hands.
Especially in Queensland, well known for being the banana state. Yes. Excellent. So Girl Clumsy asked the question, so when can I get my house electricity running on antimatter?
I love this idea, and it is sort of the idea is it could be the ultimate clean energy generation. But like I was just describing, harvesting enough antimatter to actually power anything reasonable, you have to put more energy in than you can possibly get out. So you have to think of it in terms of that equivalency. So the only way we currently know to produce enough antimatter to do experiments is to put an equivalent amount of energy in. So it would be very, very tricky to do. The only place that's really able to be done is in these special reactors like the Large Hadron Collider. There's a couple in America, relativistic heavy ion collider, which is similar to the LHC, but it's a straight line. These are really the only places where we can put enough energy into a small enough space to get enough antimatter out to do something sensible with.
So you were saying before about matter and antimatter being like the opposites of each other, like the mirror images of each other. So and you're saying before that we haven't seen these halos of gamma rays that are being given off if matter was interacting with an antimatter galaxy, let's say. If there was, let's say a long, long, long way where there was an antimatter galaxy with antimatter planets and antimatter everything else, if we don't know if antimatter falls up or down, do we think that it would respond like normal chemistry? Could there be an anti-you and an anti-me, as in the chemistry that makes us up in antimatter?
Yeah, so this is one of the things that's actually, excuse me, being tested at the moment. So currently, when we do physics with antimatter, we operate under the assumption that all of the laws of physics and therefore chemistry and biology and everything would be the same. So we assume that antimatter interacts with gravity the same as ordinary matter, and we assume that it does chemistry the same as ordinary matter. So based on our current knowledge, yes, that could well be the case. If you could have the same conditions to occur on an anti-Earth somewhere hypothetically in an antimatter galaxy, that could be, you could have anti-humans and an anti-dog, and anti-birds flying around. Yeah, so that's the assumption that we currently operate under. The experiments that are going on at CERN will tell us whether or not that is actually the correct assumption or not.
And do you think that with the missing of antimatter, like all this antimatter that seems to be missing from the universe, that's going to, once we work out where it is or why it doesn't exist, that's going to like open up physics as we understand it? Like we'll sort of, pardon the pun, blow physics up?
So I think the thing which will really change our understanding of physics kind of as we know it is really getting to the bottom of why there was more matter made in the Big Bang than antimatter, this idea of charge parity violation. Because this is the same kind of process that would go into producing dark matter. So dark matter, we don't know what it is. We only observe it through its interactions with gravity. And there's lots and lots of theories that say, well, dark matter must be some kind of particle, kind of like antimatter, that maybe it interacts somehow with what we currently see. And maybe during the Big Bang, there was some other kind of breaking of symmetry, the same there was this breaking of charge parity violation, this charge parity symmetry, which gave us antimatter. Was there a breaking of another kind of symmetry, which then goes on to give us dark matter? So that's one of the big ways that if we can understand that, that will change what we know about physics. If antimatter does anti-gravitate, I'm not sure the impact that will have, but I think that would be quite an incredible thing to discover. It would be very, very interesting to see where that would go.
So with the LHC, the Large Hadron Collider, being like the big experimenting device for antimatter, are there more plans in the future of even like the larger Hadron Collider, or what's the next big experiment for antimatter?
Yeah, so the Large Hadron Collider isn't really just antimatter. The antimatter is kind of an offshoot of the Large Hadron Collider, but this is one of the biggest experiments, arguably the biggest experiment in the world, depending on who you talk to, although I think LIGO challenges that. But there is a plan for an even bigger Hadron Collider. I think it may even be called the Even Bigger Hadron Collider. So either they could create a new, bigger ring. So currently the Large Hadron Collider is a big ring, and it's so big it crosses the border between Switzerland and France. And the idea is to build an even bigger ring and to use the Large Hadron Collider as an injector to fire particles into that bigger collider. The other option is to change slightly the infrastructure currently at the Large Hadron Collider and start putting heavier particles in. So you can put in a particle which is heavier somehow. You could exchange an electron for a muon, and you can naturally somehow get more energy out. You put more mass in, you get more energy out per collision. So those are a couple of ideas that are currently being floated. It's obviously a massive undertaking. So the Large Hadron Collider, it's still producing results, and it has many years to go yet, but that's where it's going.
Brilliant. Thank you very much. If there are no more questions, you can always ask Dr. Fiona on Twitter, and you can ask on Facebook as well. We'll get the questions, or you can always contact us at education@icra.org, and we get all the questions that antimatter you want answered to Fiona. Dr. Fiona Panther, thank you very much for coming tonight and chatting to us all about antimatter. And yes, we will see you in the future.
Yeah, thank you very much.
Thank you very much.
Thank you. Good night.